Okay, so we've been talking about the first and second derivative and the maximum and minimum values of functions. And so far we've looked at relative maximum and relative minimum. So what I want to look at today is what is called absolute maximum, absolute minimum. So if I have a function, let's say I have a function that looks like this. Okay. So we'll pretend there's my function. All right, I can see three places on this function where I have relative extreme points, right? I have a relative maximum up here. I have a relative minimum here. And I have a relative maximum here. But notice, for the maximum points, one of those maximum points is the absolute highest point on the function. This one right here. All right, this is the absolute highest point on the function. So we call that the absolute maximum. All right, now this function doesn't have an absolute lowest point because this function continues down in both directions. If I were to, let's say, flip it this way, all right, then I would have a point down here on this function, which is lower than every other point on the function. And this would be considered an absolute minimum. Now, when you're looking at a whole function, all right, you're not necessarily going to have absolute extreme points. But if I take a function and I restrict it to a closed interval, all right, so far we've only been looking at open intervals. So if I have a function, let's say, that looks like this, all right, this is a function that doesn't have an absolute maximum because it continues up forever. And it doesn't have an absolute minimum because it continues down forever. All right, if I impose an xy axis on this, and I say I am interested in this function from, let's say, let me see if I can do this straight, from A to B. So I'm interested in this function on the closed interval from A to B. And I suppose it would be helpful if I named this function. We'll call it f of x. All right, then basically what I've done is I have cut the function here, and I have cut the function here. All right, so when I look for the absolute highest point and the absolute lowest point, all right, in fact, let me do something. All right, I am interested in the red portion of this function only. There we go. All right, in that interval. So the absolute lowest point happens here, right? This is the lowest. And the absolute highest point on the function happens here. All right, this is the highest. So notice, in this particular case, the absolute lowest point happens at a relative minimum, right? So that's a critical point. So whatever that value is in that interval, whatever that x value is, x is a critical point there. The highest happens at one of the endpoints. Now that could be the case, might happen at an endpoint, might happen at a critical point. So when we're looking for absolute extreme points, right, we start by finding all the relative extreme points, and then we look at the value of the function at those relative extreme points and the endpoints of the interval. The relative extreme points have to happen inside the interval. All right, so I can probably cobble together a definition here for you, right? So an absolute maximum right, so what are we going to call an absolute maximum? Well, it is the highest point on the function absolute minimum is the lowest point on the function All right, when we're looking for absolute maximum and absolute minimum, if we have a closed interval, then those are going to exist. All right, so on a closed interval, losing track of my pen here, on a closed interval, absolute extreme points are guaranteed. All right, so if you have a function on a closed interval, you're guaranteed an absolute maximum and an absolute minimum. All right. On an open interval, not so much. So if you have an open interval or you have just a function on its domain, all right, then you might have an absolute maximum or an absolute minimum, or you might not. All right. So as far as method goes, let's talk about how we find these. And I need more boards, so let's move that up. Go back there. Okay, so I have a couple of problems here. All right, let's take a polynomial. All right, we'll start with a polynomial. All right, so this is g of x is x to the third plus 3x squared minus 1. And we're going to look on the interval from -1 to 3. All right, and the instructions here are to find the absolute extreme points. All right, so step number 1 is absolute extreme points could occur at critical points. So the first thing you need to do is find the critical points. All right, so that means find g prime. That's going to be 3x squared plus 6x. All right, I need to set that equal to 0 and solve it. I can factor out a 3x, and I'm left with x plus 2. So that's going to give me x equals 0 and x equals -2. All right, now the next thing I need to do is I need to check to see if any of those critical points are inside my interval. All right, so step 2, are any of the critical points in my interval, so -1 to 3. All right. So in this case, x equals 0 is in the interval, right? So x equals 0 is in the interval. X equals -2 is not in the interval. All right, so any point that's not in the interval, we're going to discount. All right, so for x equals 2, come up here, we're going to kind of cross that. Let me make that smaller. I don't like that being so big. Okay. All right, so we're going to discount that one. All right, so now the third thing I have to do is test the endpoints of the interval, right? The endpoints. All right, which are x equals -1 and x equals 3, along with any critical points that are in the interval. All right, so any critical points in the interval -1, 3. So that means x equals 0. And when I say test, I mean plug them into the function. Basically, plug into the function. All right, so I'm gonna come up here. All right, my function is, and I'll rewrite it up here, g of x equals x to the third plus 3x squared minus 1. So I need to figure out what is g of -1, right? That's one endpoint. I need to figure out what is g of 3, that's the other endpoint, and then also g of 0. Yes, that is the critical point that's inside the interval. Now, I think I did this math already. I did. Okay. So, g of -1, right? If we plug -1 into the function, -1 cubed plus 3 times -1 squared minus 1. And if you drop that in your calculator, you should get 1. Yes, okay, just double checking. G of 3. Yes, g of 3. All right, we're going to do 3 to the third plus 3 times 3 squared minus 1. And if you drop that into your calculator, you should get 53. And then the last one is g of 3. Okay, let me fix that. G of 3. Oh, I wrote that in the wrong place. All right, let me swap these two. Sorry about that. Put 0 over here. Okay, and then g of 0 is going to be 0 to the third plus 3 times 0 squared minus 1, which is going to be -1. All right, now these are the function values. So when we look at the function values, we're looking for the largest and the smallest. So this is the largest. This is the smallest. All right, so the absolute maximum point is what occurs at 3, and the value of the function is 53. The absolute minimum it occurs at 0, and the function is -1 there. All right, now I actually did graph this, so let me pull up my calculator. Let me just verify that you're seeing my calculator. Yes, you are. Okay. All right, so I'm going to turn on my calculator. This is what the function looks like. All right. Now, if I restrict the function to the interval that we're looking at, which is right here, -1, -3. So if I go into my window and I make the x min -1 and I make the x max 3, even without changing anything else, I can see, right, where, or at least in general, where my max and mins happen. Okay, I can't see the top, right, because this kind of throws off the top of the screen here, but now that I know what that maximum value is, I could come here, let me see, my smallest y value, let's make that like negative, just to pull that up a little bit. I'll make that -5, and I'll make this 60. All right, so now when I graph this, you have a little bit better idea. You can see how high up the maximum value is. All right, so you can verify this on your calculator if you want to. All right. Okay, so I have a few. Whoop, actually, that should have, yes, brought back the. Again, still trying to get used to the new switcher. All right, so I have a problem from 4.4. Now, as far as the homework goes, 4.4, I'm just going to give you problems like I just showed you here, where I give you a function, I give you an interval, and I say find the absolute maximum and minimum. But I just thought I'd throw in what an applied problem would look like from this section. We're going to do the applied problems from the next section. So give me just a second here. I did in your book on page 315. So let me just, okay. All right, once again, I'm not going to flash the book on the screen because I want to be able to put this up on YouTube. And if I flash the book on the screen, I'm violating copyright by doing that. So I wouldn't put the book up on the screen in class when I was doing a problem. So I'm just going to read the problem, give you the page and problem number like I normally would. And we'll do it that way. So let me get some clean real estate here. And this is going to be page 315, number 43. All right, so you can follow along at home. And I am going to read the problem to you. This has to do with the average speed of a vehicle. So the average speed of a vehicle on a stretch of Route 134 between 6 a.m. and 10 a.m. on a typical weekday is approximated by the function. All right, so this is f of t is equal to 20t minus 40 times the square root of t plus 50. For t between 0 and 4, all right, where f of t is measured in miles per hour, all right, so f of t, I'll keep going this way, f of t is in miles per hour, and t is in hours. T is in hours. With t equals 0 corresponding to 6 a.m. All right, so t equals 0 is 6 a.m. Okay, so that's all the details from the problem. So now, at what time of the morning commute is the traffic moving at the slowest rate? And then what is the average speed of the vehicle at that time? All right, so we have a function that represents the average speed of a vehicle. All right, we are constrained between 6 a.m. and 10 a.m., that is when this function is valid. All right, so if 0 is 6 a.m., then t equals 4 is 10 a.m. These are the constraints in the problem. All right, so this over here, our closed interval, is what we call a constraint. All right, and all a constraint is it's the situation that constrains the problem, right? That says we have to be within these limits. Now, with this problem, and the one that I showed you before, the constraint is just an interval. Right? We're going to see in a little while what happens when that constraint is a little more than an interval. All right, so I want to find where the traffic is the slowest. So that means I want to find an absolute minimum. Okay, so in order to find an absolute minimum, I first have to find the critical points. So I'm going to take the derivative, so f prime of t. All right, so the derivative of 20t is going to be 20 minus the absolute value of 40 times the square root of t is going to be 40 times the derivative of the square root of t. All right, so I am going to start going with, you guys know how to do this. All right, so there's the derivative, and the derivative of 50 is 0. All right, so I'm going to clean this up a little bit. All right, so I have, what do I have? I have 20 minus, so the 2 and the 40 are going to reduce, so that's going to be 20 over the square root of t. All right, and then to get all of the possible critical points, I have to combine this. So that means multiplying over here by the square root of t over the square root of t. So I'll have 20 square root of t. I'll do it in 2 steps because you can't ask me questions here easily. All right, and then when I put this together, I have 20 square root of t minus 20 over the square root of t. All right, so there's my final form. All right, now in order to find the critical points, again, this is a rational function, so I have to look at the top and the bottom. All right, so I take the top off, 20 rad t minus 20 equals 0, and I take the bottom out, rad t equals 0. All right, so if I solve this one, so I have 20 rad t equals 20. Divide both sides by 20. And I have rad t equals 1. Square both sides, that means t equals 1. So there is one critical point. And then over here, just square both sides, and I get t equals 0. All right, so this one, t equals 0 is good, right? That's part of the closed interval. T equals 1 is also good. That is also part of the closed interval. All right, so now I need to test the endpoints of my intervals and all of my critical points, because all of my critical points are in the interval. All right, and I go back to the function to do that. So f of 0, all right, so that is 20 times 0 minus 40 times the square root of 0 plus 50, and that is going to be 50. All right, now 0 is an endpoint. It's also a critical point. So I killed 2 birds with 1 stone there. T equals 1. All right, so f of 1. That is going to be 20 times 1 minus 40 times the square root of 1 plus 50. All right, so 20 minus 40 is minus 20. Plus 50 is 30. And then the other endpoint, which is 4. So f of 4, 20 times 4 minus 40 times the square root of 4 plus 50. All right, so 20 times 4 is 80. The square root of 4 is 2 times 40 is 80. So that's 80 minus 80 is 0. So that is 50. So remember what we're looking for here. Where is the traffic the slowest? All right, so this is the lowest value. All right, so this is where the traffic is the slowest. All right, so now to answer the question, the first question is the traffic is slowest at t equals 1, which corresponds to, well, let's think about this for a minute. If t equals 0 is 6 a.m., then t equals 1 is 7 a.m. All right, to 7 a.m. So the traffic is slowest on this stretch of the road at 7 in the morning. So the next question asked, what was the average speed, right? The average speed well, that is the value of the function at t equals 1, right? So that is going to be f of 1, which is 30. All right, the average speed is 30 miles per hour. All right, so as far as what you're going to see in the homework, I'm not going to throw you any applications from this section because I'm more concerned with you being learning to calculate in this section. All right, in the next section, which is 4.5, I'm combining this all into one video, by the way. 4.5 has some more interesting problems. So let me, again, get some clean screen here. And I am going to take a look at 4.5, which I'm going to do two problems. The first one is on page 322, so let me just get there. 322, and it is applied example 2, and this is a problem we've played around with before. All right, it has to do with making a box. All right, so page 322, applied example 2. I'm going to read it to you. It says, by cutting away identical squares from each corner of a rectangular piece of cardboard and folding up the resulting flaps, the cardboard may be turned into an open box. If the cardboard is 16 inches long and 10 inches wide, find the dimensions of the box that will yield the maximum volume. Okay, so let's take a look here and let's draw a picture. All right, so we've got a piece of cardboard. It's hard for me to draw straight lines on the screen. But then again, it was hard for me to draw straight lines on the board also, so I guess we're not really missing anything here. Okay, so there's my cardboard. So the first thing that the problem says is that the cardboard is 10 by 16. All right, so let's make the longer side here 16. Right, that goes from there to there. And this is in, I think, inches. What did I say? Yes, inches. All right, so let's just do this. And 10 is down here. All right, so there's my 10 by 16 cardboard. Now what I want to do is I want to pull out of each corner a square. All right, so we're going to take out of each corner a square. The same size square out of each corner. And then fold up what's left, right? So I'll have the bottom of the box is this dotted rectangle inside. Okay. All right, so I don't know how much we're going to take out because that's what we have to figure out. So we're going to call the length of each side x. Now again, we've set this problem up before. We've done it a couple of times. So I'm going to assume at this point that you have this all figured out. Right? So I'm going to put all these x's in here. All right, so if this whole side is 10 and I remove x from here and x from here, I've removed 2x, which makes the inside dimension here 10 minus 2x. And if this whole side is 16 and I remove an x from here and an x from here, then this inside dimension is 16 minus 2x. Okay. All right, so I can write an equation for the volume, right? The volume of a box. Let's say the volume of a box is V equals length times width times height. All right. Let me just check something here real quick. All right, if you hear a humming in the background, I'm going to apologize. My furnace boiler is in a closet across from where my studio is, and that wall is not completely soundproofed. So I'll double check the sound before I upload this and make sure that it's not interfering. I don't think it is, though. All right, so where am I? Okay, length times width times height. So I can write an equation for the volume of this box, right? If I fold up the sides, I'm going to see if I can do this. If I fold up the sides, this is going to be an open top box. All right. Not quite. All right, so we have something more or less like this. It's not the best box in the world, but the height of this box is x, right? That's that length there. The base is 10 minus 2x on one side and 16 minus 2x on the other. All right, so that's how we get the box. So I can write an equation for the volume of the box, which is length. So we'll say 10 minus 2x times width, 16 minus 2x, times height, x. All right. Now, we need to figure out the constraints for x, right? What is the maximum that x can be? What is the minimum that x can be? Well, the minimum that x can be is kind of obvious. That would be 0, right? If I take nothing out, right, the minimum that x can be is 0. So x has to be greater than or equal to 0. But what's the maximum that x can be? And yes, if x is 0, I don't have a box. That's fine. All right, well, the shortest side of this piece of cardboard is 10. So the largest that I could make x be is if I were to bring it all the way to here. All right, in which case I'd simply be folding the cardboard in half. All right, so that would make the maximum that x could be is 5. And I'm sure I'm hearing some of you asking, well, why did I choose that side and not this side? All right, because if I try to make x the middle of this side, which is 8, I don't have a square anymore, and we have to take out a square. So the largest square that I can take out of this is going to be 5. If I tried to take out 8, right, I would be further out than the middle of the box on that side. All right. So my constraints right here are 0 to 5. All right, let me get my box out of the way because I'm going to this out of the way. Now that we have the equation. Okay. All right, so I have to, now I have a function and I have an interval. So now I have to figure out the critical values, all right, which means I have to take the derivative of this. I do not want to take the derivative of this the way it is currently showing, okay? So I'm going to multiply all this out. I'm not going to go through the details of it. Y'all can go through the details of it at home. All right, I'm just going to tell you what it is. So v, this is now a function of x, right? If I multiply this by this, and then multiply x through it, I'm going to get 4x to the third minus 652x squared plus 80x. All right. Okay, so there's my v. Okay. And I need to take the derivative of this. So v prime. I hope I did that right. 26. 13 and 13 is 26. And then 26 times 2 is 52. That's right. Okay. You'll see when you look in the book what the calculations I just did in my head are. All right, so I'm going to take the derivative of this. All right, so that's going to be 12x squared minus 2 times 52 is going to be 104. And then that's going to be 80. All right. So now I can take out a, no, I can take out a 4. Everything divides by 4. All right, so when I take out a 4, because I need to set this equal to 0, and honestly don't want to have to factor that. All right, so if I divide out a 4, just divide everything by 4. I'm going to have, move that down. I'm going to have 3x squared minus 26x plus 20 equals 0. All right, at this point you can go through whatever your favorite method of factoring is or solving this. You could use the quadratic formula. I am going to factor it. This factors into 3x minus 20 times x minus 2. Okay. All right, so I'm going to end up here with, as far as critical values go, 3x minus 20 equals 0, x minus 2 equals 0. So this is going to give me x equals 20 over 3, which is, all right, let me see, that's going to be 6 and a third, right? 6 and 2/3. So I'll just say 6.67 if you put that into your calculator. And then this one's going to give me x equals 2. All right, so I've got my 2 critical points, but remember, one of them falls outside the interval. All right, so if I come up over here, this one right here, I don't know why my red is so fat. Why is my red so fat? Ah, that's better. Okay. I see. I changed the opacity before and not the... Okay. All right, anyway, so that one is outside the interval. All right, so this one we get to throw a line through. This is the one that we want. This is the one that's inside the interval. All right, so now I just have to check. Now, okay, I have to check just in case. All right, but we already know, because of the way we set up the constraints, that if x is 0 or x is 5, we don't have a box. All right, so x is 0 is going to give me 0. X is 5 is going to give me something that's not optimal. All right, so, oh no, it's v, not f. All right, so v of 0 is 0. That we know for certain. V of 5, well, let's see what happens. If I put 5 in here, I have 10 minus 2 times 5. Well, that's going to give me 0 also, isn't it? All right. 16 minus 2 times 5 times 5, and that's also going to be 0. All right, so that works out. V of 2, all right, if I plug that in, I have 10 minus 2 times 2. I have 16 minus 2 times 2 times 2. So that's 4, so that's 6. That's 4, so that's 12. And that's 2. All right, so if I multiply that out, I get 144. Yeah. All right, so if I multiply that out, I get 144. All right, so this right here is my solution. All right, that's the only one that gives me a box. So what I end up with is the dimensions of the box. Right, the dimensions of the box are going to be 6 by 12 by 2. All right, since x is 2, x is 2 here. That means we're taking 2 inches out of each corner. All right. So the dimensions of the box are going to be 6 inches by 12 inches by 2 inches. And the volume is going to be 144 cubic inches. All right, and this answers the question. Okay. All right, I have one more example that I want to do, and hopefully I'm not making this video too long. Let's get some clean screen here. Okay, so the next example I wanted to do because it's a little bit different than the other ones, and this is on page 324 in your book, and it is example 4. And for those of you who are going to be engineers out there, one of the things you might be engineering is a can. All right, so I have here Betty Moore Company requires that its corned beef hash containers have a capacity of 54 cubic inches and have the shape of a right circular cylinder. I'm going to draw a picture in a minute. And it's to be made of aluminum. So determine the radius and the height of the container that requires the least amount of metal to build. So this is something that you might actually be considering, right? You need to make a container that has a certain volume. So I could have now a right circular cylinder. They just mean something that looks like this, right? A can, basically. A can is a right circular cylinder. All right, so the radius would be measured this way. All right, so I'm going to do it this way. That would be the radius. The height is the height of the can. Now, the thing is, all you know is the volume, right? The volume has to be 54 cubic inches. So the question is, do I need a tall, skinny can? Do I need a short, squat can? Is there something in between? All right, that is going to use the least amount of material. Okay. All right, so we need to figure out the equations for this. Now, keep in mind, you'll be able to look up, if you don't know what the volume of a right circular cylinder is, you can just look that up. All right, when we're talking about the amount of the material that's being used, well, that is the material that makes up the wall of the can and the top of the can and the bottom of the can. So the top of the can is a circle. All right, so let's talk materials for a minute. All right, so material. All right, the top and the bottom are circles. The area of a circle is pi r squared. All right, and we've got two of those. All right, so we've got two of those. So I'm just going to say times 2. Times 2. And then the wall, all right, the wall of the can is, if I were to, let's say I were to take this can and I were to cut it down the side and I were to spread it out, you would have a rectangle. Okay. The height of the rectangle is the height of the can, right? That would be h. The width this way is going to be what happens when I split this circle and I open it up, right? So that is the circumference of the circle, right? So this is the circumference. Of the circle. So the circumference of a circle is pi times the diameter, or pi times twice r, so 2 pi r. Okay, so we have the circumference of the circle is the width, the height of the cylinder is the height. And then we also have, so that makes the area in here, what is the area going to be, right? The area is going to be 2 pi r times the height plus these two circles. So the surface area, S, of this can, which represents the amount of material, all right, so the material is the surface area. Okay, so the surface area is going to be the two circles, so twice pi r squared plus the area of this rectangle, the wall of the can, which is going to be 2 pi r times the height. Okay, now we're trying to minimize the amount of material that we want to use. So we want to minimize S, the surface area. So this is what we want to minimize. But I have a problem here. I have too many variables. I have S, which is my function. I have R and I have H. So I have to deal with that. All right, I have to get rid of either R or H. And I have a way to do that because we know what the volume of the can has to be. All right. So the volume, let's talk about volume for a minute. The volume of a right circular cylinder is the height of the cylinder times the area of the circle, all right, times pi r squared. All right, so if I know the volume, which I do, it's 54 inches. And I know the formula, and I would like to get rid of H. All right, I have a choice of getting rid of either R or H. Because I have an R squared and I have an R, we can't get rid of R. All right, so I only have one H. So I want to take this equation and I want to solve it for H. Right, so H is going to be 54 over pi r squared. All right, so now I'm going to take this value for H and I am going to plug it into that equation for H. So this is going to give me then S equals 2 pi r squared plus 2 pi r times 54 over pi r squared. Now I can lose some stuff here, right? My pi's, those are going to go. I have one r that's going to go with one of the r's there. So I end up with s being 2 pi r squared plus 2 times 54, which is 108, over r. And this right here is the equation I want to minimize. So this is what I want to minimize. Okay. All right, so I need a little more room and I'm almost done. All right, so now I know what I want to minimize. All right, so let's come over here. I'm just going to rewrite it over here so I can keep everything together. So s of, this is now a function of r, is 2 pi r squared plus, now keep in mind, in order for me to take the derivative of this, I need to have this written as a power function. So I'm going to write it as 108 r to the negative 1. Okay, so I need to take the derivative, s prime. So I bring the, r is the variable, remember, bring the 2 down, so I would get 4 pi r plus, I bring the negative 1 down, so I guess that's actually a minus, isn't it? Minus 108 r to the negative 2. All right, so I need to fix this because I need to find out where this is 0. So 4 pi r minus 108 over r squared. And then I need to multiply over here by r squared over r squared to get a common denominator. So that's going to be 4 pi r to the third over r squared minus 108 over r squared, which is going to be 4 pi r to the third minus 108 over r squared. Okay. All right, so I have that all put together. And now to find my critical values, I've got to check the numerator and denominator, just like always. All right, so 4 pi r to the third minus 108 equals 0, and r squared equals 0. Let's deal with this one first. R squared equals 0 means r is equal to 0. If I go back up and I look at my can, right? If r is equal to 0, then I don't have a can. I just have like a straight line. All right, so we can eliminate this one. We can as soon as I get my pen back, we can eliminate that one. We can eliminate this one right away because if r is 0, I don't have a can. All right, so let's come over here. All right, so 4 pi r to the third, add 108 to both sides is 108. I divide both sides by 4 pi. And I'm going to put this in the calculator in a minute. R to the third equals, oh, wait a minute. No, that's, I'm not going to put that in the calculator yet. All right, so, yeah, no, that's right. That's what I want to do. R to the third equals 108 over 4 pi. And then, again, I need to solve this. So I've got r to the third, so I'm going to take the third root. So r is going to be 108 over 4 pi to the 1/3 power, or the cube root power. So I need my calculator. Let me just, yep, we're good. All right, so let's turn this back on. So I need to do 108 divided by, now I have to be careful here because those of you with a newer calculator ROM aren't going to have to worry about this, but you make sure you put all the parentheses in there in the right place if you have to do that. There's pi. 4 pi to the power 1/3. And we get we get 2.0, I'm going to round that off, 2.05. Okay. Let's go back to the, all right, so 2.05, 2.05. All right, so now we know what the radius of the can has to be. All right, so our can has a radius of 2.05 inches. All right, so what about the height? All right, the height well, I have an equation for the height. You can see it just at the top of the board here, right? The height is 54 divided by pi r squared. All right, so the height is going to be 54 divided by pi times 2.05 squared. So again, I'm going to go back to the calculator. All right, and we're going to work this out. So 54 divided by, and I need everything in parentheses here, pi times, what did I say? Hang on. Pi times 2.05 squared. So pi times 2.05 squared. That should do it. So the height is, again, if I round this off to 2 decimal places, 11.66. Okay, so the height is going to be 11.66 inches. All right, I'm going to stop here because I think this is long enough at this point. So I will post a homework assignment. Is going to be for 4.4 and 4.5. And I just realized I didn't switch that back. Let me just switch that back real quick. Oh, yeah, there it is. Okay. All right. What was I going to say? All right, so the homework is going to be for 4.4 and 4.5. I'm not going to put up another video this week. This finishes off what we need to do this week. I will see you all on Monday, and have a good weekend.